Means of random samples and introduction. As you learned in Chapter 7, we estimate population parameters by collecting a random sample from that population. We use the collected data to calculate a statistic, and this statistic is used to estimate the parameter. Just as we did in Chapter 7 with p-hat, we now examine three characteristics of the behavior of the sample mean: its accuracy, its precision, and its probability distribution. By understanding these characteristics, we'll be able to measure how well our estimate performs and thus make better decisions. Now, we're going to need various mathematical symbols, and you guys have seen these before, but I'm going to remind you what they mean. So remember, parameter, those are numbers that come from the entire population. We usually don't know parameters because it's hard to take a census and find out info about a whole population. Now, statistic, these are numbers that we get as statisticians based on data. And so in other words, we take a sample of the whole population and we calculate something. Now, we're going to be interested in this video in the sample mean and the sample standard deviation, the population mean and the population standard deviation. Sample mean is when so basically, like if you have like a group of people and you take a sample of them, like a smaller group, you calculate the mean of some characteristic they have, say like they run a race and you calculate the mean running time. We're going to be looking at an example like that. That's represented by X bar. Now, if we were to look at the whole entire population and find the mean of the whole population, that's represented by mu. Similarly, we have S and sigma for our standard deviations for the sample and the population. Okay, now, what are we going to be doing? We're going to be using the sample mean to estimate the population mean. So we don't necessarily know the population mean when we look at a whole giant group of people, but we can take a sample mean and use it to estimate a population mean. The reason why the sample mean is a useful estimator for the population mean is that the sample mean is accurate and with a sufficiently large sample size, very precise. The accuracy of an estimator, you'll recall, is measured by the bias, and the precision is measured by the standard error. So we're going to be using these two words in this video. The short version of it is our sample mean actually is a really pretty good estimate of the population mean, which we'll find. Now, we're going to do a simulation, and in our simulation, we'll see that the sample mean is unbiased when estimating the population mean. That is, on average, the sample mean is the same as the population mean, a very good estimator. We're going to also see that the precision of the sample mean depends on the variability in the population, but the more observations we collect, the more precise the sample mean becomes. So if we're looking at people, the more people we get in our sample, the more precise our sample mean is in general. Now, we're going to do a simulation to understand this better. So how is our simulation going to work? Or what's the scenario? We're going to look at a population that consists of all the finishing times of men who ran a mile race in 2013. Sorry, it's a 10-mile race, otherwise these times would be very slow. Okay, as in most such races, data are carefully collected on every participant. Rather than showing you the histogram of the finishing times for all 7,128 runners, we're going to look at a normal model. We found that basically the distribution closely followed a normal model, so what you guys are looking at is not the histogram of these running times, but just like the normal distribution of the times. So what we found is that the mean time is 91 for the population, the entire population, so we're using mu to represent that, and that the standard deviation was 16 minutes. Remember, standard deviation represents spread, so it's like how far from 91 typically are our running times, and that is 16 minutes. Okay. Let's go back to this table. So we used mu for population mean and sigma for population standard deviation because we took the whole population and calculated these values. Now, if we took a smaller group, like some subset of the 7,000-ish runners, and calculated the mean and the standard deviation for those smaller groups, we would have X bar and S instead of mu and sigma. Okay. Now, what are we going to do in our simulation? We're going to randomly sample 30 runners. So we take some of the runners and calculate the average of their finishing times. Then we're going to do this over and over and over again, a whole bunch of times. Okay, so If we do this, we're going to be interested in two questions. What is the typical value of the sample mean? In other words, when we draw 30 people at random and calculate the mean running time, what do we typically get? Are we getting 91 or numbers very close to 91? If we are getting numbers really close to 91, then our sample mean is unbiased. 2, typically how far away is the sample mean from 91? In other words, how much spread is there in the distribution of sample means? The spread helps us measure the precision of the sample mean as an estimator of the population mean. Okay, so what you're looking at here is a summary, a dot plot that shows you what happened when we took a sample of 30 runners, calculated the mean running time of those 30 runners, so a sample mean, and then repeated this process over and over and over again, a whole bunch of times. So each dot represents one of the times that we did this. Let's take a look. So this dot right here that's just isolated at 80, that is the sample mean when we took 30 runners one of these times. So we took 30 runners, calculated the mean running time, and we got 80. Now notice there's only one value there. Most of the dots are closer to 91. In fact, they're really clustered together near 91. All the sample means are within about 10 minutes of our true mean for the population of 91. Now this is kind of cool because we know that the population mean running time for everybody was 91, and when we took the sample of 30 runners all these times, we kept getting numbers that are pretty close to 91. This was our normal distribution of the actual running times of all the runners. Notice how much more narrow this is when we took the sample means. We didn't even get any means that are like way out here. Much more narrow, less horizontal spread in this dot plot of sample means than the actual distribution of running times for all the runners. When the mean of the sampling distribution is the same value as the population mean, we say that the statistic is an unbiased estimator. This appears to be the case in our simulation because both the mean of the distribution of sample means, this over here, and the population mean are both about 91 minutes. So we're going to say that we have an unbiased estimator. Now, if we had taken a bunch of samples and gotten a number different than 91 for the mean over here, so if this was not centered at 91, then we would have a biased estimator, and that would mean we were probably drawing our 30 people in some kind of biased way. Now, the standard deviation of the sampling distribution is what we call the standard error. The standard error measures the precision of an estimator by telling us how much the statistic varies from sample to sample. So if we take a sample of 30 people and take a sample of 30 people again and keep doing this over and over again, how much variation are we seeing in these different samples that we take in terms of the mean that we get when we calculate the mean? For the sample mean, the standard error is smaller than the population standard deviation. So you can see over here that for our sample means, we have very little horizontal spread. We're getting numbers really close to 91. Over here, we have a lot of horizontal spread. So these are to scale to help demonstrate this. So more spread here, less spread here. We're going to see how to calculate the standard error soon. What happens to the center and spread of the sampling distribution if we increase the sample size? So if we draw instead of 30 runners, like 50 runners or 100 runners, and we make a bigger number. Take a minute to think about what you think might happen. So what we'll do is we're going to start over with our simulation, but this time we'll take a sample of 100 runners and calculate the mean. We're going to pretend like we do this over and over and over again. So we keep taking 100 runners and calculate the mean running time of those 100 runners. We're taking these people from the group of 7,000-ish runners that we looked at initially. Now, if we do this, or I'm showing you guys what happened after doing this, we get this dot plot, like right here. And the mean is, again, right at around 91. And then we have a cluster of dots all squeezed together like this. The picture is to scale again. By to scale, I mean in scale with the original normal distribution we looked at, so that you can show how there's like not much horizontal spread here. Okay, let's compare this to what we had when we had 30 runners. So over here we did sample size of 30 runners, and over here it's sample size of 100 runners. Notice that the graph on the right has less horizontal spread than the graph, the dot plot on the left. These dots here don't even make it to 80, don't even make it to 100, and these ones over here spread out more. Okay. In fact, if we keep increasing the sample size, so we go from 100 to 400 to 900, our graph gets has less and less horizontal spread. It's like every time we take the sample, we get a number really close to 91. So our sample mean ends up being super, super close to our population mean. We get closer and closer the more people in our group we look at. I think it should be intuitively clear why this would be the case. You can take a minute to think about it. What have we demonstrated with these simulations? Well, because the sampling distributions are always centered at the population mean of 91, we have demonstrated that the sample mean is an unbiased estimator of the population mean. We saw this for only one type of population distribution, the normal distribution, but it turns out this is the case for any population distribution. We'll see this in another video. We have demonstrated that the standard deviation of the sampling distribution, which is called the standard error of the sample mean, is smaller when based on larger sample size. So when I say standard error, I mean the amount of horizontal spread, and it gets smaller the bigger the sample size we use. This is true for any population distribution. We can be a little more precise when talking about this. If the symbol mu represents the mean of the population, and sigma represents the standard deviation of the population, then what we've seen is that the mean of the sampling distribution is also mu. In other words, x bar is also mu, and that tells us that the sample mean is unbiased when estimating the population mean. And 2, the standard error is sigma over square root of n. Now with some of these formulas, they're a little bit complicated, so we're going to use this for our standard error. We'll see that in the future. This tells us that the standard error depends on the population distribution, is smaller for a larger sample size. So if you plug in a bigger n value here, sample size number, that makes the denominator of this fraction bigger, which will make the entire fraction smaller. So as n gets bigger, the standard error gets smaller if we're using this formula for standard error. It's just a key point. For all populations, the sample mean, if based on a random sample, is unbiased when estimating the population mean. The standard error of the sample mean is given by this formula. So the sample mean is more precise for larger sample sizes because for a larger sample size, this number gets smaller.